Okay, today we're talking about composite and inverse functions. So composite functions, in the past, we've done some things with operations on functions. We had f plus g of x, f minus g, fg, which is multiplying, or f over g. But now we're dealing with composition, f of g, which this is important. This works from the inside out. And so inside out means we're going f, g, the g function goes into f. And so theoretically, you've done this, everybody's done this before. Um, so let's take a look at an example, and then we'll talk about finding the domain and range. The domain of the composite function has to be in the inner function, and then that has to be in the outer function. So this means I'm doing f of g of x, which ultimately means f of x squared plus 2, which means I plug x squared plus 2 in for my x. Make sure to use parentheses when you plug it in. I can then simplify. It asks me for the domain and range of the composite function. Domain. When I take domain, one thing that's really important, I always want to use do not do any simplifying when you first plug it in, and use that unsimplified version. Because sometimes you'll square roots and it'll get rid of them, but it had to go through that square root first, so you restrict domain is restricted by that square root. This case, it doesn't matter. I can square everything and add to it. So the domain is negative infinity to infinity. The range. This is a squared function translated up 4. So the range, I guess it should include the 4, is 4 to infinity. The vertex is at 0, 4. That's example 2. Let's go on to example 3. Consider these two functions. Find the domain and range of the functions f of g of x and g of f of x. So that's f of square root of x, which equals square root of x. That goes in for the x squared minus 1, which can simplify to be x minus 1, or maybe absolute value of x. If I want to be technical, it's absolute value of x minus 1. The domain of this function, I have to use this unsimplified version. So I got the square root, and that is, so that means it has to be 0 to infinity. The range, that's going to keep growing. If I plug in 0, I get a minimum of negative 1, and this will grow to infinity. And it also asks me this time for g of f of x, which is g of x squared minus 1, which is square root of x squared minus 1. And I cannot simplify that. The domain of this function is, so I can't have a negative in the square root, which means negative infinity to 1, no, to negative 1, and 1 to infinity. If I'm bigger or smaller than those ones, it is going to be too big, or too small. My range, if I plug in the 1, because -1 squared is 1. So like 1/2 squared, 1/4 minus 1 gives me a negative. But the negative numbers squared become positive, and -2 squared is 4, minus 1 is 3. We can square root 3. So my minimums come here at this 0, -1 and 1. Those are 0. If I plug in larger things, I get square root positives in the square root, and that goes to infinity. Okay? That is our composite functions. Inverse functions is our next section. And inverses, remember, inverses undo a function. So inverse notation, we can see it like this. I don't love this notation, but that's what it is. That means the inverse. It doesn't mean to the negative first power. Inverses essentially are switching y and x, or there is this very, very important property of inverses. And it is that f of f inverse of x and f inverse of f of x, so it has to work both ways, both equal x. And we'll show one where that works out later. Inverses also are reflections over this line, y equals x. That's this one. So what happens when we switch x and y. Okay. To check if a function's inverse will be a function, you use the horizontal line test. So we checked function with vertical line test. We check its inverse with horizontal line test because that'll be vertical lines on that inverse. So let's say I want to find the inverse of this function. I'm going to change f of x to a y. And usually I don't write this, but since I'm showing you an example, I will once. And then I switch x and y. That's step 1. Very important step. Now step 2, which is the harder one, is solve for y. So I'll multiply both sides by my denominator. Giving me 3. And I'm distributing that. I'm going to move the y's to one side and everything else that doesn't have a y to the other side. Giving me I'll then go ahead and factor out a y from the left side. It's a very important skill of gathering everything with a variable together and factoring it out. I'll then go ahead and divide by my whole set of parentheses, the 3x minus 5. Those cancel. And my final answer for the domain is y equals 1 plus, or for the inverse, y equals 1 plus 2x over 3x minus 5. That's the process of finding an inverse. Important thing with domain and range, or with inverse functions, when we find an inverse function, we simply switch the x and y. Sometimes we will restrict the domain on the original function to keep the inverse as a function. So this one does not have this particular one. Okay, so let me say that again. When we take the inverse, we switch the domain and range of the original function, just like we switch x and y. This one, its domain is negative infinity to infinity. And its graph, we should know, looks like this. Why doesn't it have an inverse function? It doesn't pass the horizontal line test. So I will restrict the domain of the original, which basically means I'm getting rid of half. I can keep the 0 because there's only 1 point there. So I'm now going to set my domain equal to 0 to infinity. And my range is then, well, my range actually didn't change. We'll just figure it out. Find the inverse if the domain is restricted. So the inverse, switch x and y, subtract 1, x minus 1 equals y squared. I'll take the square root. And generally, when I take the square root, I get a plus or minus. But my new domain is 1 to infinity, and my new range is 0 to infinity. And the only part that's in that range is the positive case. So essentially what I'm doing is I'm deleting the negative, and I don't need to write the plus. So that becomes my inverse function. We'll talk a little bit more in depth about restricted domains coming up. So, find the inverse of the function. So this is a parabola with a vertex at 1, 5. That means if I'm just trying to find the inverse, I do not need to restrict the domain, but if the inverse needs to be a function, then I have to restrict the domain. So this one, I'll just start by finding the inverse. Switch x and y. I will add 5 to both sides. Giving me x plus 5 equals y minus 1 squared. I will square root both sides. And then I'll add 1 to both sides. And we get an answer that looks like... Now that is not the inverse function. Okay, that is the inverse. If you want the inverse function, and I will argue that the book notated this wrong, you should only have the inverse function has to be a function. That's only the plus case. Or only the minus case, but... Okay, find the inverse of this. This one gets a little bit harder. We switch X and Y. I can go ahead and solve this for Y. Um, but I kind of have a problem. It's not equal to zero, so I can't just use the quadratic formula. So I've subtracted X from both sides. And I can use the quadratic formula now. Except I have this really funny thing. C is -1 minus X. So when I do the quadratic formula, I get -2 plus or minus the square root of 2 squared, or 4, minus 4 times A times C over 2 times 1. So I get -2 plus or minus the square root of 4 plus 4 plus 4x over 2. 4 plus 4 is 8. So I distributed the 4 for the second part. I can take a factor of 4 out of that and square root it to reduce my radical to be 2. So that's 2 plus x. And I can reduce a 2 as long as I do it from all 3 terms, giving me -1 plus or minus the square root of 2 plus x. And this is my inverse. That is something you may have never done before. And I agree that I cannot call this f inverse of x because it's not a function. Okay. Given the correct inverse functions for the two above functions by restricting their domains. So this is having us go ahead and restrict the domains. So the first one, I just want that side of the parabola, so the domain of the original is 1 to infinity. My second one, I mean, that's the normal way. If you look at the answer in the book, they kept the other side of the function. They said the domain was ne negative infinity to 1, which does work, which means I would just get rid of this plus here on that. This one, the second one, has a minimum point or a vertex here at -1, -2. If you're going to keep that side, which is what the book chooses, negative infinity to negative 1, it seems odd that they kept that size. And again, all that does is get rid of my plus. Okay, because the other side is gone. So when I reflect this over the line y equals x, I end up with an inverse that's in this purple. Should look, no, that was not right. Should look like this. Yeah, that's a reflection over y equals x. Okay, and that is functions and inverse functions and function composition.